Hello, I'm Mr. Singleton, one of the Associate Directors for Science for Outward Academy, and this lesson is a physics lesson all about internal energy. So we're going to actually have a look, this is the specification, we're going to have a look at what internal energy is, and then we're going to look at this temperature change and something called specific heat capacity. And there's an equation here which you don't need to remember, but you do need to apply. So you need to know what all of it actually means. As a pre-starter, I just want you to have a look at which one of these situations you think has the most energy. So either that hot coffee, or hot cup of coffee, or the cold Coke, or other drinks of that variety. So quick one, which one has the most energy and why do you think that is? I'll give you 30 seconds, off you go. Right, what we're going to do is we'll come back to this at the end of the lesson. Just keep it in your mind, which one you think has the most energy and why. So if you are doing this lesson in school, then please put the title in your books, Internal Energy and Energy Transfers, with today's date. If you are doing this at home, please make sure you've got any distractions away from you. You have a pen and paper or some revision cards, and you can just put that on the top. Now, if you're using revision cards, remember this is for a physics exam, so make sure you know that they are your physics revision cards, and this is paper 1. So this is the exam which is generally in May, or at least the first exam that you sit. The challenge for today is to explain what two energies make up internal energy. So that is the first part of this lesson, just what two types of energy make up the internal energy in a substance. The aspire is to be able to calculate the change in thermal energy when we heat or cool a substance. Now, I've talked to this in the first lesson about the three states of matter, and it's just something that confuses some students in exams. So I just want to know what the three states of matter are and what state does liquid rocket fuel change into when it combusts. I'll give you 30 seconds to have a think about it. Okay, so the three states of matter are solid, liquid, and gas. And the state that liquid rocket fuel changes to when it combusts, it goes from a liquid to a gas. The first bit then, internal energy. Now, internal energy just describes the total of the potential energy which is in a substance and the kinetic energy. So we talked a bit about in a previous lesson about particles moving around in a gas. Now they have kinetic energy, so it's that kinetic energy and the potential energy. So the potential energy is the energy needed to separate the molecules, kind of break the bonds. So kind of the energy within inside them bonds, and the kinetic energy is the motion of the particles. So think about a solid, probably doesn't have as much internal energy or kinetic energy anyway. The particles that have as much kinetic energy as they do in a gas because they're not moving around as much. So it is all of that. The internal energy is the sum, or the total of the potential energy plus the kinetic energy, and that is stored in the particles. So if you were ever asked to calculate it, then you just need to take the total of the kinetic energy and add it to the potential energy, and that will give you your internal energy. That is basically the two different types of energy in internal energy. So now we're going to have a look at this aspire. So we hopefully know that when we heat something up, we change the energy within those. So we increase the speed of those particles, therefore they have more kinetic energy, and that can either raise the temperature, or then it can change the state of matter. So it can either go from a liquid to a gas if we're talking about the combustion in the rocket fuel. Now, what determines the increase in the temperature? Well, what that depends on is what is the mass of the substance that's heated, or the type of material, or the energy input into the system. So if I have a very small amount of water, if I take this mass of the substance, if I have a very small amount of water and I heat it, it will heat very quickly. But if I have a large mass of water, it wouldn't heat as much. And also different materials will heat at different rates, and that's something called their specific heat capacity. So some materials will take on heat very quickly, and some materials won't. And then it's also about how much energy you put in. If I only put a very small amount of energy into a big, massive tub of water, it's not going to heat up that much. So that's what this all depends on. And that's how this equation comes about. So this is the equation to work out the change in thermal energy. So it's dependent on the mass, which we talked about with a small cup of water and a large cup of water. It's also determined by the specific heat capacity of the substance and the temperature change, and that will tell you the thermal energy. Now, as for every equation, you need to know what each one is measured in. So mass is measured in kilograms, as always. The specific heat capacity is in joules per kilogram per degree Celsius. We're going to come on to that in the next couple of slides. And then the change in temperature is in degrees Celsius. Now, just remember, there are different ways to measure temperature. So there's Fahrenheit and there's Kelvin, but in this case, we're using degrees Celsius like most people do. That little triangle there, that just means a change in. Okay, so that just means a change in temperature. Just try and help you with this. The specific heat capacity of a substance is the amount of energy that is needed to raise 1 kilogram of that substance by 1 degree Celsius. So if you think you've got a kilogram of water and you want to increase it from 10 degrees to 11 degrees, it's the amount of energy that you would need to do that. So 1 kilogram of water actually needs 4,200 joules of energy, and that would heat it up by 1 degree. This yellow box here is the types of questions that you might get. So calculate the energy needed to warm up 2 kilograms of hot water, and it's being heated from 20 degrees Celsius to 90 degrees Celsius. And we've got the specific heat capacity of 4,200 joules per kilogram degrees Celsius. So this is how you would tackle this question. You would write the equation. That equation is found on your physics equation sheets. You do not need to remember it. So it's energy equals mass times specific heat capacity times by the change in temperature. Then you can start to plug in the numbers. So we've got energy, which we don't know, times by the mass. In this case, it is 2 kilograms, times by the specific heat capacity, which is 4,200. And then the change in temperature, it was already 20 degrees Celsius and it's gone up to 90 degrees Celsius. So it's changed by 70 degrees Celsius. And then you times that together and put it into your calculator, and then you get 588,000 joules. And that is your equation. On the next couple of slides, I've just shown you how I would do that on a whiteboard with a couple of different scenarios. So please have a look through and make sure you understand it. So this is a standard question that you would get in the exam. And remember that this equation is on your equation sheet, so you don't have to remember it. So the question is, what is the energy needed to heat 7 kilograms of an object with a specific heat capacity of 20 joules per kilogram degree Celsius from 10 degrees Celsius to 12 degrees Celsius? So I put down my equation, so the energy needed. Now I'm looking for the mass. Okay, so here is my mass, which is 7 kilograms. And we have to remember that C is specific heat capacity. So that's this number here, times by 20. And then this triangle, this delta, means change, and then change in temperature. So it's from 10 degrees Celsius to 12 degrees Celsius. So the change in temperature has been 2 degrees Celsius. And then you would put that into your calculator, and please do use your calculator in your exams. 7 times 20 is 140, times by 2 is 280, and you have to remember the joules on the end because it's in energies measured in joules. Okay, so this one's a little bit harder because it involves rearranging the equation, and I've said that I will go through each of these every time with you just to help you with them. So this time it's asking what is the specific heat capacity, okay, of an object which needs 400 joules to heat 10 kilograms by 10 degrees Celsius. So again, write out your equation. So E, energy needed, equals mass times the specific heat capacity times by the change in temperature. Now we have the energy, so let's plug in these numbers because this gives us a mark in the exam. 400, and then I've got my mass, so I can put that in times by 10. I don't know C because that's a specific heat capacity, but it is only by 10 degrees Celsius. So change is already 10 degrees Celsius. Now I would, if I was you, work this out. So 400 equals 10 times by 10, which is 100, and that is times by C. This is where we rearrange. So in order to get rid of this 100 and get C by itself, I would divide this by 100, and whatever I do to this side, I have to do to this side. So now I've got 400 divided by 100, which is 4, equals C. So the specific heat capacity would be 4. And remember then you need to put on the unit, which is 4 joules per kilogram degrees Celsius. And that would get you 3 or 4 marks in the exam. Now it's over to you. You've seen me do it with a standard question and you've seen me do it rearranging questions. So this is your time to have a go at the question. So this is calculate the temperature increase if 100 kilograms of water for a bath is heated with 2 times 10 to the power of 7 joules. And you need to answer this with 4 significant figures. So remember, put in the equation, then put your numbers in, then start to rearrange, and then remember the 4 significant figures. I'll give you 3 minutes, off you go. Okay, you've got 1 more minute. Right, let's talk through this then. So you should have written the equation, which is E equals mass, or sorry, energy equals mass times specific heat capacity times by the change in temperature, which is the thing that we're trying to find out. Then you put in your numbers. So the energy we know is 2 times 10 to the power of 7, and the mass of the water was 100 kilograms, and the specific heat capacity of water is 4,200. And then we are timesing that by the change in temperature, which we don't know yet. So the next thing you would do is work out what 100 times 4,200 is. So then it's a bit easier then just to rearrange it. So we've got 2 times 10 to the power of 7 equals 4, 2, and then 0, 0, 0, 0 times by the specific heat temperature change. Now we can rearrange it. So what I want to do is get rid of that big long number there. So we would divide that. Let me just have a look. It's 420,000. So we divide 420,000 times by the temperature change by 420,000. But then we also have to do the same on the left-hand side of that equation. So it would look like this. So it's 2 times 10 to the power of 7 divided by 420,000. And then that will give your answer, which for 4 significant figures is 47.62 degrees Celsius. So that comes to the end of this lesson. I want you to just have a look at these exam questions. So what is meant by internal energy of water? That's question 1. I'll let you have a go at that now. So I just want to know what that's made up of. It's simple 1 mark, but it is from an old exam question. What is meant by the internal energy of water? Next question. So if the water is heated until it boils, the temperature remains constant at the boiling point, so it'll stay at 100 degrees Celsius. Explain the effect on the internal energy of the water and the movement of the water particles. So that's 3 marks. What's the effect of the internal energy? So you're heating it. What's going to happen to the internal energy? And what's going to happen to the movement of the water particles? I'll give you another 30 seconds. Okay, question. The energy transferred to the water is 302.4 kilojoules. The temperature of the water is increased from 20 to 100 degrees Celsius, and the specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. Calculate the mass of the water in the pan. So you're going to have to rearrange this equation, but first remember there's the equation, so it's on the equation sheet, but first remember plug in your numbers that you know and then rearrange the equation to try to get the answers. I'll give you one more minute to work it out. Okay, we'll go through the answers. So number one, what is internal energy? So it's the kinetic energy plus the potential energy of all the water particles or molecules, 1 Mach. So if you heat that up and it's boiling, the internal energy increases 1 Mach because there's an increase in the potential energy, 2 Machs, and the water particles will move further apart or become less dense. And then the equation you should have rearranged. So you should have done 302.4 times by 1000 equals m times 4,200 times 18. It was 80 because it was 100 minus 20. And then that would have got you a mark. So that's a mark if you've done that. Next mark is if you then rearranged it correctly. So you divided it by the 4,200 times 80. And then the last mark is for putting 0.9, which gets you, and if you just put a 0.9 this time, it does get you all of the marks. Okay. So if you're making revision cards for this, this is what I would suggest you include. Internal energy is a sum of the kinetic energy and the potential energy within a substance. And then you need to know, well, you don't need to know this equation, but you need to know it's there on the equation sheet. The change in thermal energy is the mass times the specific heat capacity times by the temperature change. And what specific heat capacity is the energy required to raise 1 kilogram of a material by 1 degree. Okay, so practice those calculations, practice rearranging that equation as well. Make sure you understand it. You're doing a super job. Keep it up. Well done.